So it's my pleasure to introduce Ricardo Trindade. He's a professor of geophysics at the University of São Paulo in Brazil. I've had the pleasure of knowing Ricardo since 2004 when I first started as an undergrad in São Paulo. So I've had several classes with him over the years. And it's really nice to be able to start working again and then bridge this gap between Liverpool and São Paulo. We're starting some new projects. Ricardo is going to be talking about some of the work he's been doing in archeomagnetic and speleomagnetic, which is a new term that's being coined here for the record that has of the South Atlantic Anomaly. With that, I'll hand it over.
Thank you, Leo, and thank you, everyone. I'm very happy to be here. I was talking to Leo about the speleomagnetic things that since all people working on magnetism or archaeological artifacts call it archeomagnetism, so maybe you have also speleomagnetism for those magnetism of speleothems. And it's interesting to say that this thing started here. It was Alf Latten that started speleomagnetism, and he was a lecturer here, professor in Liverpool for a long time. And everything started with a paper by him in 1979. So the idea of this talk is to talk about what we've been doing to map the South Atlantic Anomaly from the record that lives in rocks and archaeological artifacts for the past thousands of years. So the South Atlantic Anomaly is this big dent in the geomagnetic field. Usually it's defined as the region encircled by the 32,000 nanotesla line. So this is the whole thing that is in blue here is the South Atlantic Anomaly nowadays. Interestingly, it has this huge major anomaly here, but it has also this smaller feature that is kind of starting here at the southwest coast of Africa. And some people are saying that it's splitting somehow. And if we see the maps of the evolution of this anomaly, it started as a very small anomaly here and then drift to the west. So the idea is from the paleomagnetic record in Brazil and Africa to understand how this anomaly evolves during the time that we don't have the observatories to follow this. So the idea was to understand or try to understand the origin of this anomaly, the age when it started, and also if this is a persistent feature of the magnetic field, if it's a recurrent, if there are some times in the past thousands of years that this feature disappeared. So that was our main goals at the beginning of this project. Here is the anomaly as it is in 2015, and here's how it has evolved. The center of the anomaly has evolved in the past decades. So this talk, first I'm going to show the South Atlantic Magnetic Anomaly, how it is defined. Then I'm going to talk about reverse flux patches, the Archeomagnetic record, mostly from Brazil, Speleothem record from Brazil as well, and I'm just mentioning a bit about the volcanic record because there were very nice works coming from people from here, and the origin and recurrency of the South Atlantic Anomaly. So this is a series of maps of the magnetic field made based on the Geomagnetic 1 model, showing how this anomaly has evolved since 1590 until 2005. This was a paper by a student in our lab long ago, and they show that the anomaly started as a very small anomaly here in the western coast of Africa, and then started to migrate and increase in size, so intensifies at the same time it migrates to the west. And this was it in 2005, and nowadays we see that it's even bigger and has this small new feature in the east. And it's interesting that since we started to measure the magnetic field on Earth with Gauss and Weber, what we see is that it's decaying at more or less 5% every century. But at the same time, what we see is that the behavior at the different hemispheres of the Earth is completely different. When you look at the southern hemisphere, we see that the magnetic field is decaying very fast, and while in the northern hemisphere is more or less constant. So so it seems that there is the reverse flux is going completely crazy in one part of the Earth, and it's completely normal, more or less the same at the other side of the planet. So there's something happening, and eventually what we can see is that the amount of and the intensity and the amount of reverse flux patches in the southern hemisphere is increasing with time. So we decided to study those features through a PhD thesis of this guy, Felipe Terranova, and together with Hagai Amit from Nantes University. So we have in the magnetic field when we go down to the core-mantle boundary, and we do the map of the magnetic field at this interface, we see that there are lots of features that are of higher intensity. Those are the normal flux patches. They are here, they are very close, usually close to the tangent cylinder. And we have also at lower latitudes some features that are reverse. So the field in those positions, they point opposite to the magnetic field, general magnetic field at that hemisphere. So we have those features that are called reverse flux patches. The idea since the work of Bloxham in 1986 is that those features are related to expulsion, upwelling of field lines across the core-mantle boundary, so forming those features of reverse flux. And the idea is that those features, they could be related to the origin of this South Atlantic anomaly. So to test that, Felipe did some modeling to see which kind of features at the core-mantle boundary would generate features that are like the South Atlantic anomaly at the surface of the Earth. So to generate a feature like the South Atlantic anomaly, you don't need just one patch, you need a combination of different patches, including a normal flux patch, influencing the anomalies to make it not only nucleate at that position, but also make the movement we see from the geomagnetic record. So that was the one of the papers that Felipe published about the reverse flux patches and the relation with the South Atlantic anomaly. Something interesting we saw from the archeomagnetic models, meaning the geomagnetic models that go back to 3,000 years in this case, is that those flux patches, they have preferential longitudes and latitudes as well. And when we compare those longitudes and latitudes with the seismic structure of the mantle, we see that those longitudes and latitudes that are preferential for the flux patches, they are also, they coincide with zones of low velocity zones at the lower mantle. So, and so there are some colleagues that suggest, Tardono is one of them, Felipe himself, that those features are somehow related to differences, lateral differences in heat flux at the core-mantle boundary. So somehow the mantle exerts a influence on these features, and they are somehow originated from those features that are related to the mantle. So after analyzing those archeomagnetic models, we also realized that we had very few archeomagnetic data in Brazil. So we started a study through Wilbur and Galvan, but together with Andy, on the archeomagnetic results from Brazilian sites. So South America at the time, this is a from Geomagnetic 2015. We were responsible for only 3.8% of the database for archeomagnetic results. But and at the same time, exactly Brazil and Africa that have the biggest variation in the magnetic field. So most of this variation is based on very few results. So this was the map at the time. Then we started to collect samples from buildings from Salvador, Rio, and São Paulo, and also from South Brazil. And I'm going to show some results from South Brazil. So we collected samples from all the postcards in almost every one of those villages. It was very fun at the time. We'd go to do research. We'd go into those museums or famous colonial houses to collect those samples.
They were happy with you drilling holes in them?
Yeah, that was the most difficult part.
I can imagine.
So we had, it took us some time, some years to convince the historical patrimony agency that we were going to do something. Because for them, it's very hard to understand that we want to get a piece of one of those buildings to study the magnetic field of the Earth. So for the archaeologists, it's not really something that they understand straight away. But then finally we got the permission. So this is a fortress in Salvador, the Bahia. So we collected samples from the fortress itself. That's the dates from 1696. And the lighthouse was built much after. So we have 2 points, archeomagnetic points from this building, from the fortress itself and from the lighthouse. This is the residence of one of the first mayors of Salvador. And the dating we have for those bricks is the dating of the house itself. So it's and there are some bricks that they stamp the date of the brick in the brick. So we have a very good age control on those archaeological materials.
Much better than.
Yeah, much better than when we're running land sometimes. And those are the sites in the south. Those are the Jesuitic missions. They were abandoned at the beginning of the 19th century. So we have a very small age range as well. When we collected samples from Brazil, Argentina, and Paraguay, from all those settlements. And in the south, we have some old farms that were also studied by archaeologists. And so we collected some samples from there. And finally, almost all those sites, they produced amazingly beautiful RI plots with very nice results. And we applied very strict criteria for selecting those samples. So we believe that we have very good results that are able to show the things we want to show, like the very small changes related to the arrival of the anomaly. Once we get those results, we start to compare with the results we had from the rest of South America. And this is the thing that we had at the beginning. It's a really mess. The results are all around. Then we started to apply some criteria. We were inspired by Patterson et al. 2014. Greg is here. And this the idea was, okay, let's see what the best data will give us. I know that there are lots of people that prefer to go for the whole data set. And then, okay, we're going to average out any problems with this. But the idea here was exactly the opposite. Let's see if selecting the best results based on those parameters are going to give us a more coherent evolution. And that's what we had after applying the criteria. So it means that we have a much more coherent evolution based on the results that we considered that are the most reliable ones. And it's interesting that now that if we plot those results, the intensity of the field against the ages, you're going to have for almost all of them a very nice evolution. Note that here we don't have the latitude correction. So here they are placed and relocated to the city of Pelotas. So all of them follow more or less the same trend, but you're going to see that those bluish colors, they are from Argentina and Chile. They are out of the influence of the South Atlantic Anomaly. And this red and yellow dots are under the influence of the South Atlantic anomaly. So they have a difference that is outside the error bar, suggesting that there is an influence of the local anomaly on those results, not only the location of them in terms of latitude. Then what we have done is that we have calculated the intensity of the relocated site minus the intensity of the dipole, the G10 for that position. And what we see is that what we would expect is that if the field was essentially dipolar, this result would give 0 or around 0. But then what we have is that we have something that is around 0 until about 1800, and then it goes really down this value for the sites that are under the influence of the in the location that the anomaly passes. For those sites that are in Argentina or Chile, we have not that many. We have 1 or 2, but they are more close to the 0 point. So it means that those sites are influenced by known or strongly known dipolar, and they are this behavior starts around 1800. So it means that eventually the influence of this strongly known dipolar field related to the South Atlantic anomaly arrives or hits Brazil at about 1800 or even before. Then I said, okay, but we need to expand this record. We don't have archaeological material to expand this record to the past in South America. All the archaeological artifacts we tested from the original people in Brazil, they were not cooked enough. They were giving very unstable results. So we could have good results from bricks, from colonial constructions, but not from those artifacts. So it said, okay, so we need to have another material to try to go back in time. And then we started to try the speleothems. So this is a big group because we have all those people that collected speleothems for us. Some people here, here's Leo, and Johnson is a student that we share, working on the modeling of the magnetism of those particles. And here, people from IRM that were also involved in the speleothems. And here, Roger that entered the group to work in to help us with the micromagnetic images. So speleothems are those beautiful features that we find in caves, but we are particularly interested in the stalagmites, which are the features that are that grow from the base to the top of the caves, and they have it's very easy to do the stratigraphy, so they are very easy to control. They are easily dated as well. So as I said, we are studying mostly the stalagmites, which are those features, and those stalagmites, they are very interesting because they grow almost continuously, and it's very easy to see if there is a gap in the growth of the stalagmite, so we can track very easily if this is or not. They have magnetic particles all over. The magnetism of those features, they are easy to measure as well in the cryogenic magnetometer. There are two reasons that we have enrichment of magnetic particles in those speleothems. One is flooding. So sometimes the cave increases the water level, and the clay that is around the base of the cave goes and covers the speleothem. But we have also lots of magnetic grains coming from the soil above the cave and precipitating together with the calcium carbonate. So we have all those magnetic particles, and those are the particles that we use for paleomag. Those speleothems, they are all also easily dated by uranium thorium with very good resolution, temporal resolution. So we have ages that are at the decades or even less in terms of precision. And something very important is that they are the remnants in those structures is really very rapidly blocked. So somehow they provide us results that do not suffer from the same problems lake sediments suffer. That is the fact that the sediments, they usually have a signal that is moved through time. So it seems that speleothems, they can record very fast variations of the magnetic field, and that's very interesting for us because we are looking for those fast variations of the magnetic field. So here's the first record from a speleothem by Latham, 1979, showing that the variation in the declination and inclination in a stalagmite, and also the age by running thorium. So he was using exactly the same techniques we are using today, but at their infancy. So they were not as good as today, but the idea is there. Another very interesting paper, one of the earliest papers as well from Morinaga, shows that you can also try to model or make artificial speleothems using thiosulfate of sodium. So here what he did is that he precipitated thiosulfate inside his cryogenic. The cryogenic had a field. So he said he observed that after about 60 minutes, 15 minutes, the magnetization was completely blocked, showing that this is really fast. So it's almost instantaneous blocking of magnetization, at least in this kind of case, in this kind of artificial speleothem. We are reproducing this experiment by Morinaga now in the lab. So that's what we are doing. So those are our artificial stalagmites from a master student. And here's the device we are using. We are using a box with the an internal field that is more or less homogeneous. And we are precipitating those speleothems with thiosulfate mixed with sediments from cave. So we get a sediment from a cave, we mixed, and we have a system to stir this substance of thiosulfate together with the sediment, and the thiosulfate becomes solid at the when it goes below 50 degrees. So you need to keep it warm enough above 50 degrees. And then it goes to a cannula and precipitates to form those stalagmites. And now what we're doing is that we are trying several different magnetic fields. And see if we can really prove that this kind of magnetization can provide a relative pile intensity signal. So if we can model if the relative pile intensity that we can get from the speleothems can really mimic the pile intensity we get from other tools. And something also interesting about speleothems is that almost all speleothems that we studied provide exactly the same magnetic neurology. Here we have a diagram of dp against MDF that we model from the IRM acquisition curves. And each color is a different speleothem and covering the whole stratigraphy of the speleothem. So we have almost the same kind of mineralogy for each one, and that's very important for the relative pile intensity, because then we have the changes in intensity of magnetization are going to be not true related to differences in magnetic mineralogy, but related to the changes in the inducing field. Something else we are doing is we are observing those speleothems through magnetic microscopy. So this is a QDM, is a quantum diamond microscope that through a very simple setup, we have a CCD camera here. We have a diamond, which is an artificial diamond, full of pairs of nitrogen and vacancies. Then through the influence of a laser in a small magnetic field, if the magnetic field is more intense close to one of those pairs of vacancy and nitrogen, it's going to emit a light, and And the amount of the luminosity is proportional to the intensity of magnetization. So we have a map of magnetization from this kind of setup. And here's the map we have for about 2 millimeters per 1 millimeter and a half field of view. And from those dipoles, we can, using technique that we are developing together with Leo and the student, to identify all the dipoles that we have. And from this dipoles, calculate the full vector in this sample. It's interesting that here what we have done is that this speleothem has both magnetite and hematite. So we have induced a magnetic field that is very strong, about 2.7 Tesla up. And then we applied another field in opposite direction that is about 0.3 Tesla. So the idea is that all hematite that's very highly coercive would give a north direction, and all magnetite would switch to a south direction. So in this way, we could separate magnetite and hematite, but not only that, we can see where magnetite is and where hematite is in the sample at this scale. So we're talking about 2 millimeters per 1.5 millimeters. So we can see that we have both hematite and magnetite, much more hematite than magnetite. And it's very coherent with the results we have, that the magnetization we've done, half of the momentum is about to be attributed to magnetite, which is much more magnetized than hematite, and the other half to hematite. And then we apply that to two speleothems in central Brazil related to this problem of the South Atlantic Anomaly. Here I'm showing the region where we have this low velocity mantle anomaly. Here's the map of the magnetic field. Here's the location of some studies that have been done that were done in Africa, and some. Here is the position of the caves that we studied in Brazil. So in 2015, Tarduno and others, they realized that from the study of burned soil in Africa, that there were very rapid variations of the magnetic field there. And he proposed that those rapid variations were related to the South Atlantic Anomaly. So we collected those speleothems that follow and cover more or less the same time. Here's the age model. Each sample we analyzed corresponds to about 30 years or 32 years. So every sample we have, so we have a resolution of this 30 years or 40 years. And here's the results we have. Those are the Zeider worlds. Here's the Pseudo-Tillier array plot. So we always link the AF field that we use to calculate the relative value density to the field that we use to separate the component in the Zeider world. And this is the results we have from the two speleothems. This is for inclination. This is for declination, and this compared to the models, and this is for relative paleointensity. It's a bit noise because it's expected because we have small magnetization and it's a ratio, but it follows generally the data. This pink, those pink points are the data that were selected after those criteria that I've shown before. So the results from both speleothems, they follow more or less this, and they are completely different from this model, for example. So, and then based on those results, we started to see if we could also see in the Brazilian results those fast changes that were observed in Africa. And what we saw is that we can see, but they are delayed, and we saw two of those loops were delayed by 250 years between Africa and South America. And we checked using the models of Felipe if we could model this, if it's possible to see which kind of mechanisms could create a anomaly that would change the magnetic field separated by this period of time. And so we worked on the westward drift, intensification and expansion of the anomaly. And of course, the main mechanism responsible for this, the signal we saw is westward drift, but we must also include intensification expansion to explain it. So we need to have a not only the westward drift of this feature, but also its intensification expansion in the action of other reverse flux patches to explain the anomalies we see. And finally, we try to go back in time. And so we choose another speleothem that goes from 3,000 to about 5,000 years back in time. And here are the results we have. Those are the results of the speleothem. This is the result of the first one, that is the younger. Oh, sorry. Here's the what we see where the South Atlantic Anomaly is active. Here's the other results. The variation is very strong as well. But when we see the directional variation, it's much stronger in the younger parts than in the older parts. So it seems that this is a mark of the arrival of the South Atlantic Anomaly, and it matches very nicely the results that we are seeing from the archeomagnetic data. Then we went to map the reverse flux patches to see if there is a big difference between the period where we see the South Atlantic Anomaly going back and forth between Africa and South America, and the period of the South Atlantic Anomaly where it doesn't appear. In fact, it's not there, and it happens that in this time between 3,000 and 5,000 years, we have almost no reverse flux patch at the core-mantle boundary, and at this time we have plenty of them. And when we analyze the magnetic field through time, what we see is that this recent period where the South Atlantic Anomaly is present, the non-dipolar field is very strong. The dipolar field is strong, but it is decaying. Whereas in this period where we don't have the anomaly, we have much lower energy for the non-dipolar components. So it seems that the South Atlantic Anomaly is not only something that is recurrent, but it also depends a lot on the interplay between non-dipolar features and dipolar features. And so it can be absent at some times during this period. It's interesting to see that there are some studies that were done suggesting that this anomaly may be there for millions of years. But we see that even at the scale of thousands of years, it may be absent, it may be very strong. We are now working on this part of the time to see if it appears there. So the main conclusions that we have, first, is that archeomagnetic data and speleomagnetic data from Brazil suggest that the South Atlantic Anomaly in features like that hit South America at least 2 times in the past 2,000 years. Rapid changes the secular variation South America and Africa after 2,000 years, with delays of about 250 years, suggests recurrence of the South Atlantic Anomaly. But there are times, maybe during 3,000 to 5,000, that those features are absent, are not observed. So it's an intermittent process. It's a recurrent process when the magnetic field situations allows to appear. Rapid secular variation may be explained by a combination of westward drift, densification, expansion of reverse flux patches at the core-mantle boundary. These features are related to the relative strength of the non-dipolar field as well. And finally, it's interesting to say as well that speleothems are faithful recorders of the geomagnetic field and may provide a continuous high-resolution record at centennial to millennial scales. And using those microscopic techniques, we can even go to annual scale, and that would be very, very nice. I'd like to thank all of you, and I'll answer questions if you want to ask something.
So, any questions from the audience? Not Richard.
So with the speleothem, so one speleothem can take you back what, thousands of years, that annual resolution? Or
It would be
so one
nice.
speleothem that can, how far can each speleothem record? That's what I'm trying to ask.
Oh, it depends, because it depends a lot on the precipitation rate. There are some speleothems that are like 40 centimeters or 30 centimeters that go back to 500,000 years. Yeah, but those are harder for paleomagnetic people. So we are in those cases we are working mostly on the very rapidly precipitation speleothem. So what we do is that we have in a cave we have active speleothems, so we know that they are precipitating now. But we have some of the saloons or some of the places in the cave that have speleothems that are not precipitating for a long time. So we collect different places, and then we date the base and the top using running thorium. Then we know which period they are related to, and then we choose which speleothem to study depending on the main object that we have. But it's really amazing. There are some speleothems that can go back to the Renaissance reversal. Yeah, it's very hard to date because the running thorium technique goes down there.
Can you get the Lechon?
Yes, that's something we are working on. Yeah, we have a project with people from MIT to work exactly on the Lechon. In fact, there is
Tell me when I can say something.
You can say stuff.
So the top stuff, so I was obviously working on a quarter.
Yes.
On the top stuff, and we ran into this South Atlantic Anomaly before the shot for that day.
Yes.
And the thing where it showed really strongly was within Argentinian record. And Monica lost faith in that record, which seemed very harsh because when you've got a really big signal at exactly the right time, it's kind of So a South American record for that period would be lovely.
Yeah, I fully agree. I think we have found 2 caves with speleothems covering the Lechon and that are already dated. So those are the ones that we are going to try first. Yes. And the good thing is that since you have the stratigraphic record, then you can go through time and see what's exactly the structure of the event.
Just make sure you look at the couple of thousand years before the Lechon as well.
That's the idea, to go before and after, just to see how it goes.
It seems we have some questions online.
Okay.
Can you pull up the? Let's see.
Zoom is here.
Is it you there?
I have a question if I'm able to ask.
Oh,
Yeah, so we got Andy.
hi Andy.
Hey, great talk. Really enjoyed that, Ricardo. So I wonder if you have a view on. So you show, South Atlantic like anomalies happening, affecting the same region in the past, and clearly it's unique in the world today. I wonder if you have a view at all on, is it unique in are there any other similar phenomena, in the showing up in the models in other places? So
Yeah,
is it
there are 2 other features that I'm very interested on. The first one is the spike, the Levantine spike. So I'm getting some speleothems from the region around there. It's very easy because there are lots of carbonate there. So I'm going to try to. It's interesting because in fact it's a peak in intensity, and it seems to be. At first, people thought it was a limited peak, but now people divide into different peaks. And knowing the surface that it affects is also important because it's so localized. But for example, now we think that we have found the evidence for that as far as Portugal and Morocco, for example. And the other thing that I'm also interested is that that seems to be some of those minima like the South Atlantic Anomaly happening in the Pacific as well.
What time period?
It's within the last 3,000 years.
Okay. I guess I mean, the spikes were like 3,000 years ago as well, and there hasn't been anything quite the same since then. So I don't know. Is it your view that the South Atlantic is a region of especially active non-dipolar behavior?
Yeah, I think so. And the models show this. Like the analysis that Cathy Constable has done on the 2000 models together with Monica Court, they show that there's a very strong activity in the southern hemisphere, and it's really related to the South Atlantic anomaly. That's very clear.
Yeah, thanks.
I'll ask one after. Just to do with the you mentioned that the LLSVPs, and they're partly responsible for creating these reverse flux patches.
Yes.
But the reverse flux, so that's mantle timescale stuff, but these reverse flux patches are changing
That's right.
really fast. So I wondered how is that a big factor in this South Atlantic anomaly, or is it more just the westward drifts?
Yeah, in fact, it was John Todono has proposed that in 2015, but it was something that was taught before.
Gubbins result.
Gubbins results, yes.
When he did he was the first dynamo.
Yeah. And the question is, just this discussion, if those anomalies, they are top down or bottom up generated. So if the mantle has something to say about it. It seems that this lateral heat flux variation has something to do with the origin of it. So where those flux patches are nucleated, because because of this lateral gradient, we would have those flux expulsion lines. And then that's where those flux patches would be created. But then they would migrate to the west, so intensify. But based on not only the mantle control. So what the mantle control does is to say if we're going to have the potential to create those reverse flux patches at this scale, always located in the same place. That's I think that the question that Andy has made, like, do you think this is a feature that is there for a long time? People suggest that if this mantle control, if this lateral flux, heat flux gradient is important, and if it's there for millions of years, it means that we are going to have such an anomaly happening in the same region for this time scale. It doesn't mean that the anomaly is going to be there fixed, but it's going to be nucleated and will be walking around that region for a long time. So there is a paper by suggesting that, for example, one of the islands that are in the middle of the Atlantic, St. Helens, the volcanic record of the island, given the very high spread in the directions, shows that the anomaly is there for millions of years. We are now working on an island that is close to the coast of Brazil called Trindade. It's not my island, it's a military place, and not my ancestors as well. And this island has volcanic rocks that are dated by starting at 400,000 years, going up to 3 million years. So those are also interesting to test if this anomaly has passed through the same place several times. But it's do you have something to say about it? But it's that's it. So the mantle anomaly would not say that the anomaly is the reverse flux pattern would nucleate there and stay there, but it would be the first step to have those lines of field being expelled away from the core-mantle boundary.